want to look at the some wave reflection ideas. And so waves reflect differently than particles. So I'm going to bounce this to Parker. Ready? Just a golf ball. When that golf ball hits, it reflects when it hits the ground, and it reflects in a very consistent way. So yep. So the reflection that a particle goes through is really simple. Whatever angle I throw this thing in at is the angle that it comes out at, right? So if I throw it more like this, it bounces off at a different angle. Particles easily reflect. If I wanted to get this thing to you, bounce it off that wall, where would I throw it? Halfway between you and I, it would go over, it hit this thing at that particular spot, and then it come over and it'd obey the law of reflection and go right to you. Particles do that. Waves can also reflect. So waves reflect a little bit differently. I'm going to send a waveform down to this particular spot, and I notice that when it hits, it comes back, and it travels along the exact same medium. So what I want to do now is I want to show you the two different kinds of reflections that occur based on what kind of terminal end I have. At a fixed end, an end that is fixed in place, the waves are going to reflect, but they reflect inverted. They will come back opposite of the way they went in. We would say it's out of phase. So phase again represents, like, what is that waveform doing? Is it going up or is it going down? Where is it in its motion? And so we would say that a wave that hits a fixed boundary reflects inverted. Now waves can sometimes hit a free boundary. A free boundary would allow the wave to reflect. The disturbance gets to the end of it. When it comes back, though, it reflects upright, or we would say it's an in-phase reflection. I want to give you a couple of examples. Musical instruments. If you play a guitar, you play some sort of piano, stringed instrument, oftentimes the stringed instruments have a fixed endpoint, and so a wave will go down and reflect inverted. Ever been to the beach, Judah, Patty? Why you guys been up here to Grand Haven from your various locations? You guys ever get out to Lake Michigan and go to the beach at all, been into the water? You guys live in locations where the water is salty, correct? Ours is unsalted, sort of cool. But water waves, when they hit the pier, they reflect by riding up the pier and then reflect back in phase. This is like a free end. Now you notice that this says that this is not part of your quiz or exam. I'm not going to ask you to describe free end or fixed end reflections, but there are going to be some of you that are going to be doing projects that involve endpoints that are fixed or free. Okay, so that's how they reflect. Now, there's not an asterisk on this. This is what we call standing waves. There are times that I have a confined medium, a medium that has endpoints. Could be a guitar string, could be an antenna. A disturbance might set up something called a standing wave. Oscillates with a particular pattern. Now that pattern, I'm going to show you a couple of different ways of looking at this. The pattern that comes from this is due to interference. It's an interference between waves that are reflected along the same medium. That interference will produce particular patterns. Each particle of a standing wave has a unique and fixed amount of energy. And so this is a way to take information and encode it in a waveform. Now, I did this demonstration before, but I want to do it one more time, now that we're actually to the point where we can understand this. That's Slinky. Robert, will you help me with that? That's a Slinky, the big string. All right. Now, can you help me? Sure. Okay. What I want to do is I want to show you the standing wave patterns. Okay. Back over that way. I can't remember who I had help me with this before. Was it Parker? Okay. You did a great job. Not saying anything that disparaging you or anything like that. But so the idea behind this is that if I send, this is how standing waves are created. I send a disturbance down. You notice that that disturbance goes back and forth along a confined medium. Now the speed of that disturbance depends largely on things like what the what the tension is and that thing, what is the mass per unit length, density, and all that kind of stuff. But let's just say that I have a fixed medium, I send a disturbance down and I reflect it. If I have a continuous disturbance, not a pulse, but I have a continuous disturbance, if I can time it such that the new energy comes in at the exact same rate as the returning one comes back, do you guys notice what's happening to the amplitude? Can you guys see that the amplitude is getting bigger? Standing waves are due to a reflection interfering with the source of disturbance coming in. This is the first standing wave pattern. It's the longest wavelength, lowest frequency wave that will stand on this particular medium. Robert, you and I are 5 meters apart. What is the wavelength of this wave? I did this before, but we were new to this. But you and I are 5 meters apart. What's the wavelength of this? 10 meters. Now what I'm going to do is I'm going to increase the frequency. Instead of me going really slowly, I'm going to start to go at a faster frequency. And now I notice that this thing sets up a new standing wave pattern. Now, if you and I are 5 meters apart, what's the wavelength of this wave? This is fine. Right in the middle here, Kiera and Parker can see a point right in the middle that's not moving, or at least somewhat stationary. Can you see it? That's what we call a node. That's where a crest always meets a trough, and they cancel each other out. So that would be a nodal point. I'm going to increase the frequency further. So if I can go faster now, I'm going to get, I notice that there's actually 2 nodes now in between us. 2 points at which I always have a maximum destructive interference occurring. And then other locations where I get into that maximum amplitude. Okay, so these are what are called standing wave patterns. Okay, if I increase further, so I'm going to go back and forth even more quickly, and at certain frequencies, we get a nice standing wave pattern. Robert, do you want to try to get 5 or 6 of these? I know I did it before, but you want to try it?
All right. It's a lot of work.
It is actually, because I am applying a force or a distance here, and that force or a distance is work. I mean, that's probably what you were trying to say, right? That's a lot of work. It truly is. Force through. Okay, so I can do ones like this too. And so, all right, Kiera is going to do a jump rope. Can you get in there? No? Could do this all day, it's sort of fun. There you go. All right, now what I'm going to have you guys do is I want you guys to be able to do some calculations with me. So this standing wave pattern is due to interference between reflected and transmitted waves. First, if the frequency of this oscillation is 2 hertz, the rope is 6 meters. Can you guys tell me what the wavelength is? This is the first standing wave pattern that Robert and I set up. I know Simon got it, because he was the one that was giving me hands up and fingers and stuff like that. If that rope is 6 meters, what is that wavelength? What is the speed at which that disturbance propagates? Because remember, the speed is this is a disturbance that's propagating, going back and forth. If I know the wavelength and I know the frequency, can I get the wave speed? What is it? 24 meters per second. That's how quickly the disturbance is propagating. How I'm getting that is a product of that number and that number. That's how fast that disturbance is propagating. Now, the next frequency that we had set up, the rope is 6 meters still, right? It's the same length. What is the wavelength now? It's 6 meters. My question for you is, what is the frequency of that oscillation? Do you guys agree that the speed is the same? It's the same kind of rope? So what would be the frequency of that oscillation? I take the velocity divided by the wavelength. That velocity is still 24 meters per second. That wavelength is now 6 meters. 24 divided by 6, would you guys agree that's 4 hertz? So the frequency of that oscillation is 4 hertz. You notice it's double what the first one was? That's not a coincidence. Can you tell me what is the frequency, the wavelength for this one here? I want you to give that one a shot. See if you can do that one. Tell me what is that frequency and that wavelength. Natalie, I noticed that you've always been really good with the math stuff. I've seen it. Your math is really, really fine. Putting you on a pedestal right now. Could you tell me what is the wavelength for this one?
No, I didn't do it yet.
Oh my gosh. I know someone knows it. 12 meters, 6 meters. This way, would you agree it's smaller as I increase the frequency? Smaller? What is that wavelength? Thank you for trying. It's not 3. It's not 3. Thank you for trying, seriously. 3 is smaller than 6. Is there a way that you could look at this diagram and sort of break it into segments? It's 4. So I noticed that this represents 1 full wave. That portion represents 1 full wave. It's got a crest, it's got a trough. And if I think of this as divided into segments of 2, that's 2, that's 2, that's 2, the wavelength would be 4 meters.
I just got like 12 by 3 parts.
Sure. However you get there is fine. My point is that the wavelength of this standing wave is 2/3 of the entire length. You guys see it? If that's, notice the wavelength goes from 12 to 6 to 4. And if I increase the frequency more, the wavelength is going to get shorter. The constant is the speed. The speed is 24 meters per second. Could you tell me what is the frequency of that oscillation? And I noticed something, that every time, this is 4, this is 6, every time I want to get a new standing wave, I increase that frequency by that number. 2, 4, 6, the next one would be 8, the next one would be 10, the next one would be 12, and so forth. That's that pattern. Okay?